Again, we will be seeing cases on how a better design can be more or less impact. And taking this idea how a residual material, which it is a problem, can be converted in opportunity. Also, the case of that. First, when we talk about conceptual design, is block diagrams. And as I mentioned earlier, the more stages you have, without even thinking that much, you know you have a low efficiency process. Best case scenario, for example, in a reaction, you can have either 90% conversion, 80%, and if you don't know, put 60. This is my advice. If you know that a process is not good, put 30%, but whatever stage that you have, even filtering, washing, it will have an efficiency. So if you have a process with 12 stages, different things, the efficiency is very low. That's the reason, because of pharmaceutical industry is really, really expensive, because there are many, many stages. Okay, so think about that. This is the first clue of, each stage is 0.6, 0.6, 0.6, so you end up with 10% conversion at the end. Recirculation is always good, because you either play with residence time, you have a degree of freedom of a reactor, residence time. And we already talked about what happened in grinding. I hope you study a little bit more on grinding, why we have recirculation. You remember we talked about that? The recirculating load. In a grinding, in the primary grinding, you use a circulating load of 300%, 400% in order to have a more tight or closer particle size distribution. Why do we want to have a better a more narrow distribution? Narrow distribution. In an open circuit ball mill, that will be open circuit, you have a distribution like that. I'm exaggerating that. Imagine it can be either bar mill. Well, let's make a ball mill better, to avoid confusion. But if you have a ball mill, remember, also you can have primary grinding, also you can have reverse grinding. What is the reverse grinding? In this case, you feed here, you have a product here, goes to the cyclone, overflow goes out, and then you return here. This is direct grinding. Put the material in the ball mill, reduce size, and then which is over the size go as an under and recirculate. When I'm talking about reverse grinding is when you first, it's not normally in the flotation stage. You have the material here, underground, goes to the ball mill, okay, and go there, something like that. So first you classify, because only the coarse particle goes to the ball mill. This is in the cleanest section. Do you remember the circuits? Okay. If you don't, it's not that complex. It's a reverse, because you classify first and then have a particle size reduction. In either case, we're talking about recirculation. In either case, when you have a recirculation, you end up with a more narrow distribution. This is the frequency, diameter, different beam class. We prefer to use cumulative distribution. When we talk about narrow, it's more sharp distribution. More sharp distribution, it means more narrow. Why we want to have a narrow distribution? Right? This is our goal. To have narrow distribution. What happens if we have this distribution? Why our goal is to have a narrow distribution in particle size? The next stage is flotation concentration, isn't it? What happened if we have this distribution with recovery? Exactly. Do you remember? You have the recovery particles by size classes. It's an exercise that you need to do it always. 20 microns, 200 microns, it will be log scale. It's something like this. Why do we lose particles here? Why we cannot collect those particles? You took courses with Janatos. Wait. If they don't know, you explain. Any idea? You've seen that? Yes, go ahead. You also did something with particles. Well, anyway, go ahead. No, I'm talking about small. Why we lose here? Why we lose those particles? I know, too small. Why? Sorry? No, you're confusing with this one. This is the coarse particles. The explanation that you're doing is coarse particles. This is related with probability of collision. Probability of collision. In general, in flotation, a good flotation, what is the probability of collision percentage? 3%. 3% were good enough. 3% were good enough for collision. When you have 20 microns, 10 microns for a 1 millimeter bubble, you have 0.001%. The probability of collision is really slow. Really low. Okay, no worries. I know that you don't know this in detail, but you will know more in detail probability of collision. We have a very nice article on that, and we play with MATLAB, Fluent, and all that stuff. Okay? I already wrote it down. Arriagada, Vinet, Jaques, Aldonza Jaques, and Master. It's flotation particle. Look by author. Very nice. Please review it. The article. It's a new model for bubble particle collision, and we didn't do any experiment. We just took data for Roy Dow 60, 80. We took a lot of data, and we have better fitting only because in the modeling we consider the inertia of the particle. We put the density of the particle, and then we understood the relationship bubble particle collision. Okay. This is not related with process design at the moment, but I'm trying to explain in order to have better processes, to invent better processes, to have innovation, you need to understand the very fundamental things. And we have the knowledge. That's the reason because you are here. Okay? So this is probability of collision. Nana, do you remember now? Probability of collision. To make it simple, if you are in a big boat, transatlantic boat, in a cruise, big one, and there is a tiny rubber boat, you are in the boat, it generates a lot of waves, and you try to collide this rubber boat. What is going to happen? The small boat will be swept away because of the waves. Okay? We model that with COMSOL. And the people from ANSYS developed in Brazil, by the way. In Brazil, they have a very strong group in ESS, the company, remember? ESS. And they developed the model, but it was kind of, we can come back to that. Because we did it in COMSOL, the fluid dynamic See what you will see in the paper, and then we simulate this. These waves is called streamlines. When you have a moving bubble, generate liquid moving around and sweep away particles because the inertia of the particle is too small and sweep away. And regardless the mineral, platinum, gold, copper, molybdenum, whatever elements, you will see the same curve all the time. Below 10 microns, sweep away. Okay? What happened? Now Nana, it's your turn. Or, sorry, Ignacio, anything to add here? Probability of collision? Do you remember?
I mean, everything that you said is pretty much what I already heard.
You already know. Okay, you already know that. Nana, why we lose particles in the coarse size? Do you remember? Okay. Yes, we see that in the plot. Yeah, we see that. They are too big to be attached, but you're explaining the same that we can see in the plot. But you're not saying why. Isn't that? Differentiate describing something from explaining why. Sorry? Free surface. It sounds beautiful. We're talking about surface tension. It's not enough energy to what? To be stick. But the big particle has a lot of surface. We can control it with a collector. If we put more collector, and if it's more liberated, listen, if it's more liberated, more energy should be able to attach. But still, it doesn't good enough to be attached. We modify the surface with collector. Do you agree? What else? Nana, your time. Remember. Ignacio.
Well, one reason maybe that they have a lot of inertia, so they just, when they collision with a bubble, they just go through the bubble.
You mean it breaks the bubble?
It can break the bubble also.
It's very resistant, it's very elastic. We know that because we have measurement with high-speed camera. Again, we can come back to that to see those beautiful experiments. We have the high-speed camera. One clue. Induction time. Induction time. You remember now? You have a bubble that has a layer of water, and when it collides, it will collide. Now, the analogy of big ball with another big ball, it will collide. But in order to be attached, meaning air is going to be attached to the hydrophobic part of the particle. The attachment, very good said, it's because you have hydrophobic, the air bubble is hydrophobic. When you put together, they have less area, so you reduce the energy. Two droplets of organic collide and put together in a larger one because this one has too much area. Surface tension is the amount of energy that you need to create surface. Okay? Come back to induction time. You have a big bubble with a layer of water, so it collides, but it needs to break the water layer. So it requires some time to penetrate the liquid layer and get attached. That is called induction time, to remove the water layer. Okay. Yeah, this is an example that what are we expecting you to explain when we talk about that. Not only describing, coarse particle has less recovery, fine particle has less recovery. No, we are expecting a technical, sound explanation. Two things. If you increase the hydrophobicity of the particle, it will be quicker, the rupture of the liquid film. Okay? If you have more liberation, it means you have more surface, more liberation, will break easily. Understand? Okay. So most of the things for coarse particles are related with collector. The technology, such as technology with fluidization. The thing is, inject water from the top, so from the bottom, to reduce the terminal velocity of the particle, to give some little time. But I don't agree with that. Okay. You always is a rate. The larger the particle, less liberated. So less probability to break the water layer. Okay? We know that model, experimental evidence, practical, from the industry practical, we know that this shape, elephant shape, but something that is new, remember, you are in a master program. You also study new things. I want to finish with that. Depending on the frother, we can control the thickness of the water layer. So a frother can influence the induction time? Yes, nobody has studied that. So using frother, we can control water thickness, and then we can control selectivity of particle size. We've done it experimentally, we will see. And also another thing that is called entrainment. Entrainment. I will not say anything, you will see, but just to create ignorance. If you have ignorance, it's good because you learn. Entrainment. Okay. Finish with flotation particle size, come back to recirculation. So that's the reason, because we want to have a narrow distribution, because if we don't have the right distribution, we are losing a lot of money here. That's the reason, because miners produce a lot of tons for the comminution. Comminution, the KPI is throughput. They don't have an indicator of quality of the particle size distribution. And then this impact flotation. Where is the money? In flotation. Concentrator, the concentrator increase. The money is in the concentrator. Okay? Come back. So recirculation in some cases is necessary in chemical reactor. We do it a lot in order to control the residence time, the conversion. But I don't go deeper in chemical reactor here, but understanding the concept of recirculation. Or when you have reaction, separation, and on top of that, you also have services. Services are putting thermal energy, extracting heat, because in some cases, for example, an autoclave reactor is a reactor that works high temperature. You need to put energy. But then when you finish the operation, you have hot liquid. You have liquid with a lot of pressure. By the way, in the autoclave reactor, all this energy, we call it enthalpy, hot and pressure, is used to generate steam. To cool down, generate steam, and steam is energy. In general, we use a lot of steam because it's an easy way to transport energy, thermal energy. Okay? This is the plant to produce a cesium compound that was developed by a chemical engineer student. Why we start with that? Because there is a product. I'll come back to the flow sheet, I'll explain. Sorry, let me explain here. There is a product, commercial product. This is cesium formiate, which is the formula. What are the characteristics of this compound? Has a very high density. It's a liquid like a milk, very heavy, 2.3 grams per cubic centimeter, or 2.3 kilo. 2.3 times water density. So it means that it works as a stopper, as when you make holes in petrochemical. And the only company that produced this compound is an American company in Canada. The mine is in Canada, and they don't sell the product, they rent it. You know what I mean? I'm renting the fluid, and I don't know how much it costs, but there is only one producer. Why is it important? For petrochemical prospection, and also for the one that we call hydro leaching, which is leaching, making holes and making a lot of pressure for in situ leaching. So that we're going in that direction. Okay, so it became important. And look here, cesium formate is environmentally friendly. Nothing happened. Cesium is like potassium, like sodium. Okay, so we have a product. Again, whatever thing we do is not sustainable, but we have a product that doesn't damage the environment. Something happened. Throw it away. Okay? So it's relevant. Let's come back to problem. Problem. In the lithium industry, again, you go to the solar plants where lithium is concentrated from 0.6% lithium to 6% lithium. Then it's sent to the coast by truck. Then lithium plant, when you produce lithium hydroxide or lithium carbonate. We will talk about that. He wants to learn about lithium process. I will do that. During the process, you generate a brine, very concentrated brine. In some cases, 900 grams per liter. Very high concentration. It looks like an oil. But this one, we were saying, what can we do with that? And we found cesium and rubidium. They are together. It was extremely difficult to measure that because of the ions. Okay, we use ICD, we sent samples to Europe. Extremely difficult to characterize. Now I'm coming back to atomic absorption. Atomic absorption is more precise. I really like ICP, but ICP is dependent on other ions. There is a lot of interference. But in any way, we find 10 ppm. Okay? So the whole process, it can be improved because that was back to 2018. So they have an evaporator here. We use steam to evaporate concentrate. Now we can use the hot air bubbles technology. Crystallizers, ionic exchange, and now the important thing. We were able to extract cesium. There is a previous guy. In 2015, we worked with another guy using adsorption. That was, okay, you know what? It's interesting, cesium, blah, blah, blah. He won an award. He went to England to show the project, and blah, blah, blah. And because it's very difficult for selectivity from a soup of a lot of ions to extract one specific element. And we found, it was a happy accident. We found a resin selected for cesium. Looking. How? It wasn't my finding. It was a former student, chemical engineer. By the way, he works for iodine company, Koshayash. Looking, they found a specific resin that it was developed by desperation after the Fukushima accident. You know, remember Fukushima accident? The nuclear plant in Japan. And what was the contaminant, radioactive contaminant? Was cesium, radioactive cesium, remember? So a French company developed a specific, a resin, we will see in ionic exchange. In ionic exchange, you can have functional group just to fit a specific atom size, and also you generate molecules. Those are called crown ethers that have a specific size to just sit one element. And we found one. We contacted the American company who produced it and sell it. They gave us the product, and we did the isotherm of subtraction. And with this data, which is in this thesis, this is the heart. And normally you have two, because one is working in adsorption, another one is being reactivated. Okay, this is the heart. So imagine all these happy conclusions. We have a brine, which is very bad because they send it back in truck, so they cannot dispose it. They don't have more permits to put more saline solution, environmental permits. They don't have it. The only way is taken back in a truck back to the one problem. Second, look at that. Actually, we review more stuff. Even they have uranium. Even they have a very little, but they have a lot of elements. We look for germanium, a lot of elements. When we found cesium, then happy accident. The cesium is a very good product. Another happy accident. There is a specific resin. Understand? So then we went in that direction, and the rest is chemical engineering. Believe me, it's not that complex. You separate, concentrate, separate. That's it. And this plant is very small. These columns are 3 inches. It's a very small plant. So the production is too small. We start with 10. Remember, mass balance. We start with 10 ppms. It means 10 grams per cubic meter. And we are able to, this is the filter, to crystallize first cesium chloride. We didn't produce the formula. It's easy for us only the chloride as a product, crystal. We also can produce metallic cesium, but what happened with metallic cesium? What happened? You haven't seen what happened when you...
It's highly reactive.
Absolutely. When you have sodium, potassium, rubidium, explode. It's very unstable. You need to look in Google what happened. It's a crazy chemical engineer, chemical professor that did do this experiment. They put explode. It's very, very reactive. Very reactive. Even generate hydrogen and explode in the flames. So we end up with this product. It was the easy one to handle, to produce, and then we can sell cesium chloride. You understand? Okay. So this will be the process design with the mass balance. We have specific tools. We can use, for example, HAC, which I know you have you've been using it. I don't like it that much. It's, let's say, for amateurs, relatively speaking, if you compare with Aspen. Aspen is a 30-year experience for industry in general. It's very expensive. It's $100,000 per year, $100,000 per year. It can be simulated there, but in HSC you need to put data. You don't have any data. In Aspen you do have it. Okay. But anyway, just to show you, you will not end up the course with that. It's just to understand, having the boxes, the conceptual, it's more than enough. Then you can hire chemical engineers or stuff like that to have more detail. But it will not change the project. You know, it will not change the conceptual project. You will be reducing the uncertainty. Let me show you. So we start with the, you have different phases. This is done for mining projects. This is the conceptual design, which is the block diagram. And then you have, look at cost estimate 50% plus minus 3, so you have a big error. Well, it doesn't matter. It's something that I said earlier. My proposal is to extract solution, and you need 300 kilowatt hour per cubic meter. Forget it. It's too much. Yeah? It's to separate feasible things. Feasibility preliminary is okay. You need to know if it's a sack mill, if it's absorption, if it's membrane. You need to. Sometimes we call it basic engineering, but it's not really basic engineering. For them, it's more advanced. Okay? And then you're reducing the uncertainty. When you are at the very end, over there, startup operation, when you have the plant completely built, still you have problems. Especially mining has a lot of uncertainty. Other industry, other chemical plant, pharmaceutical plant, no, it's more for some reason, either constructors, there is a lot of uncertainty, and not to mention that your material also is different. BHP, they test a brand new technology. It's a good room flotation cell. It didn't work, and they have very stupid things. For example, they start with a reverse osmosis plant, and they put the maximum quality of water, but it was really bad because you cannot generate froth. It was too good, the water. No, you have 20 microsiemens per centimeter. No, this is pure water. You need to have some ions in order to generate bubbles. You know? There are other stupid things when you start. I mean, one of them was you have the feed tank, or one of them were pumping from the bottom. You have the pipe from the bottom, and then you generate hydrostatic pressure, and the liquid comes back. So the pump didn't work. I mean, the superintendent called me. What can we do here? Very simple. You just need to change the pipe and make something like that from the top, atmospheric discharge, but it will generate a vortex. So put some bubbles. I was thinking something similar. But it happens. It happens all the time. And you review the engineering. Okay, you have kinetic data, and we will use for scaling up. You have one time. You have 4 minutes for a batch test. A batch test is something like this. And we need 8 minutes to have 85% recovery, and then we will use a factor of 2.5. So the plant, which has 8 cells, 6 cells, will use this. This is the criteria. I'm not kidding. I'll show you the first meet presentation a couple of months ago. They have a demo, but we will learn what should be done in reality. Okay, but that happened. So it doesn't matter if it's Hatch, Ausenko, all of them make mistakes because they don't have them. Okay, so the idea is just telling you some of the experience that we have there. You know, it's very simple, and then you're gonna be famous. Okay? So that's the reason, because it's that high, the uncertainty. That's right. Okay, you have the idea of the uncertainty level, so there is not meaning looking for a quotation for a pump. You don't need it. You need to have only the big equipment. You don't care. I mean, that one will be 20, 30% more. It's nothing compared with the investment. Okay. Okay, yes, I don't go into detail because you have the material to study what it means. This is very important to understand. Deliverables, preliminary design, block flow diagram, equipment list, plot plan. I mean, is the view of the plan. Then feasibility preliminary design basis, PDF, process flow diagrams. Very important. Material balance, process data sheet, preliminary equipment layout. When you put the equipment, then you need to think. Sometimes you need to put balls in there. Sometimes you need to make a maintenance. You need to remove an equipment. And then if you don't think how are you gonna do that, big mistake. This is the layout. Okay, but this is enough. We'll not talk about more of that. Perhaps most of you already have this project plan. But believe me, everything that is unthinkable will happen. Everything that is unthinkable, it will happen. Let's come back to the cesium. So that was an interesting, happy accident. I will show you how the only producer in the world, again, is an American company which uses mineral ore from a Canadian mine. Okay, company is called Cabot. Pretty much the same thing in analogy lithium. In Australia, in Chile, Argentina, we have lithium as a natural brine. It's already in solution, it's already dissolved. But countries like us, like Finland, they have solid rock. What is the mineral for lithium? Spodumene. Bertie Lambert, the person who created the HSC software for process, is design and install a plant filter starting from spodumene because they want to be self-sufficient in lithium. But they start from rock. In analogy to lithium, in cesium, it happened the same thing. This is the this is the current operation for cesium production. Mineral extraction, rock, material, crushing, combination 75 micron. Remember, the smaller the size, more energy we need. Okay. The crushing it doesn't consume energy because it combines because of the cracks. You have more cracks. The smaller the particle, less crack, then you need to put more energy. Okay? But anyway, it's not a big issue. We can end up 20 microns with isoanyl and anyway. Acid leaching, temperature. Acid leaching, temperature. Crystallization, thermal process, roasting, final purification, and you end up with the cesium chloride. The same that we are producing. Okay? Those are the equipments. By the way, this is a sag mill, it's exaggeration, but it doesn't matter. Just to illustrate graphically what it means in terms of equipment, extraction, combination, acid leaching. So this is the alternative process. What is the, look, I mean, the way that we present. This is the current process, okay? This is the one that we are proposing. Waste from dry lithium carbonate plant is a waste, first thing. A waste where we need to pay to dispose, transport. It's a waste that has a cost. Concentration by evaporation, and then you have ion exchange. Those are the isotherms. We work with that. We will learn. Those are the rupture curves. When you have in a continuous, we will learn that. We need to have the isotherm and the rupture curve in order to understand how much time do we need per column. Okay. Evaporation, ion exchange, solvent extraction. I'm missing one part here, by the way, which is the precipitation. But remember, low concentration, ion exchange, PPM, higher concentration, solvent extraction, and then crystallization. Always. Okay? Look the selectivity. 82% experimental data, we did it. It was TRL4. Yes, yes, 4 is small, very small. We have very little resin. Okay. But and then you compare that, so they are kind of, they are kind of costly. But compare the selectivity with other ions, it's really good selectivity. That's because the chemistry developed a specific resin. Okay. Got it? Another case, this is the sulfuric acid plant on the top of the Preeling tower. A preel, it's, for example, you have a solution and you generate a drop. It's a very tall, and as soon as the drop is going down and you put hot air, it evaporates and produces a crystal. This is a preel from solution generated. And you will see, actually, we touch it. I don't have the video, but this size preel. Iodine, same thing. Iodine, you produce the iodine, you melt it, and then you have hot liquid iodine molten. I saw it in a company. They wait for as it's going down, the droplet, the hot droplet, liquid, and crystallize and generate potassium chloride. Same thing. You have molten salt, liquid, cool it down, and you can generate a crystal. Pellet, rounded. So there they produce by drilling. Drilling is the process generate crystal of. In this case, it's ammonium nitrate. Ammonium nitrate. Ammonium nitrate is the base for the explosives. Raw material, it's ammonia, NH4. Chemical plant to produce nitric acid. You combine both and generate this solution with acid-base reaction. Okay, and you generate ammonium nitrate, which is the base for the explosive. The largest plant in Latin America is in Mejia. We will be visiting that. What is the heart of the thing? It's kind of crazy. You have the ammonia. You need to compress the ammonia in order to put it in a reactor. You need to burn it, part of them, and you have a compressor to compress the ammonia. You burn it to produce some NO3 gas. Okay? You use this heat to generate steam. And all those equipments are coupled in a single shaft. Compressor, turbine, and 50% of the energy is recovered. I mean, you need to convert ammonia into NO2, NO3 gas in order to convert that into nitric acid. So in the reaction, we use all these heats. So the compressor is connected mechanically to the turbine. Amazing. It's a very nice. I think I wrote on there. Yes, with a single shaft. Sorry, it was written there. You have a ammonia compressor, single shaft, turbine to burn ammonia. Remember, NH4. You can burn it and generate energy. Why is important NH4? This is NH4. Why is it important? If you want to go renewable, you're generating hydrogen. We cannot transport hydrogen, we transport ammonia. Ammonia can be converted in a turbine, like CH4, like methane. It can be converted in a turbine. By 2025 in Japan, Mitsubishi, Japan, it will start an industrial plant to produce electricity. You check the number, Mitsubishi, NH4 turbine, I think it's 10 or 20 megawatts, big one. Look at that, producing a turbine by expansion. Did you find it? Mitsubishi, ammonia turbine. My colleagues in mechanical engineering, they also are doing that. And we simulate that with Aspen, by the way. Goodbye, Aspen. Aspen, I want to have this Aspen as a demo. See, as a demo. The turbine. Okay? He's the big boss of Aspen. How many days do you have? How many? Yes, students. Seven. They're building modules in Aspen. Do you find it? Yeah. How many megawatts? 40. Starting in what year? You see? Okay, so having a turbine with ammonia is something that we wanted because it starts from hydrogen, understand that? So in this plant, which is for a different purpose, this plant is to produce nitric acid and ammonium nitrate, NH4NO3, okay? So it's connected, this turbine is connected because as a product, the product that you have there is my raw material for the nitric plant. But again, this is a happy accident. And the gas is hot, and this gas generates steam. And this steam can be used to generate electricity too. This is called Brayton cycle. When you have, for example, natural gas, you burn it in a turbine. In a turbine, you burn it. The hot gas heat water, you produce steam, and this steam goes to a second turbine in a steam turbine. All of them connect the same shaft, and generate more energy. This is called Brayton cycle. In this case, we use ammonia. Fascinating. If you don't remember, same axis also has a compressor to compress the ammonia gas and go inside that. So you have, it's crazy. Fascinating. Did you know that, Ignacio? I think we talked about that.
Yeah, we talked about that.
When you're doing a process control. Did you use it with the students or no?
No, I couldn't find it like with the process sheet and also the.
Do you mean this?
Yeah, and also because the instrumentation wasn't really clear with that kind of device. So.
I mean, I'm not pretending to understand everything, but this is the process that integrates everything. My intention here is integration of different operations. That's my goal, understand. But this is so crazy. Compressor, turbine, Brayton cycle. So 50% of the energy is generated in this unit. Imagine that. 50. Okay, like it? So my intention here again was to show you the integration of energy, okay? Generation, understood the idea, okay? Not the detail, the idea. One of the easy way to integrate thermal energy is using this heat exchanger. This is the heat and plate exchanger. You can see it in our lab, assemble one, and also disassemble one. We need to organize a tour with other TAs. You to take the plate and see it. Yeah. This equipment, heat and plate, is used usually, for example, for food industry, for it's called high temperature treatment. UHT treatment. It's not pasteurized. Pasteurized is when you keep it with long time in a high temperature. The milk, for example. In this equipment, it goes to 120 degrees, 2 seconds, and then cool it down in 3 seconds. This thermal shock, kills all the microorganisms. If you check your box, your milk box, it will say if it's not reconstituted from a Russian plant, it's not reconstituted. If it's real milk, you will see treatment UHT, ultra high temperature. It's not pasteurized. So then we use those equipments, and the thing that we want to do is look for either the energy that you have, flux, and also the temperature, and actually you play with different equipments, and we look pinch method, because here, for example, I can integrate these two equipment. And this is the pinch method. You have implemented that also in aspect. So you design a circuit, and then you have hot and cold currents, and then you plot like that. The method is called pinch method. And then you put the heat exchange, and you recover energy. And if you recover energy as a balance, you're reducing the amount of energy. That's it. So for us, it's very easy. For example, since you are minor metallurgical engineers, in the electrowinning process, you have I think I have it here. No, it's not here. It's at the end. I'm not sure if I have it here. It's not here. It's here. Okay, in short, you have heap leaching on top of here, heap leaching. When you irrigate with a solution, it's 5% sulfuric acid. It takes 2-3 bonds. The heap leaching pile, it can be 10 meters high. It makes the leaching process 60%, 60-65% extraction. Then you end up with a solution. Solution goes to solvent extraction. We'll skip that, solvent extraction. But listen up here. And then the solution that contains copper, goes to electrowinning in a process which is really hot. You put steam. You put steam to heat up process. And just having here 1 degree, 2 degrees to 10 cubic meters per day is gigantic amount of steam that you need. Okay, so I think I told you once I was asked to review one of the. You want to review the steam production because you use fuel. Okay, then I saw the heat exchanger. Remember, as a consultant, never give solution. Just listen, and then proposal. Otherwise, you're gonna. It happened to me. So, in this case, you will see our equipment. Usually, this you put back all this, and then you have a very long screw because you can add more plates, and then you increase the area easily. So this heat exchanger, I think it was this high, and I say stupidly easy. You just need to buy plates. You don't require consultants. 4, 5, doesn't matter. You put plates and you increase the amount of area, and then you transfer more heat, and you reduce the consumption. Okay. So this equipment is really cool for recovery energy. Of course, you need to put pressure for liquid. For gases, it's different. For gases, we use heat pipes. For low temperature, we use other technology. Okay. Understood then, as a concept, the pinch method. Of course, I think this is too much for going for Aspen. I think I'm happy to having the turbine. The turbine is fine. Okay, again, this is the conceptual design for the, let's say, single axis. Single axis. This is the compressor for the ammonia. Air compressor, nitrous gas compressor, and the wave gas turbine is expanded, and then this steam turbine heat is used to generate steam, and then all of them connected in single shaft. Compressor, okay. And after that, it goes to a catalytic reactor. Okay. But the one that I want you to see is this. Compressor, turbine, and gas generation. This is in more detail. And then once you generate the nitric acid, you concentrate by distillation. Okay? I think it's time. Okay, we continue 5:30. 5:30. In the 4th floor. Okay. Now run for lunch, otherwise